Hello, welcome to the third video on the thermodynamics course that I'm doing for the channel. Today we are going to see a not very known equation in thermodynamics, which is known as the Clausius-Capeyron equation. Okay, so the important thing of this equation is that it's going to describe a system that is well under equilibrium conditions. And those conditions are going to be established from two substances that are composing the system. Okay, so we are going to work out with, well, a system that is going to be made of the same substance, but in two different phases. The first one is going to be liquid and the other one is going to be vapor. Okay, so let's consider that we have that system over here and we have the liquid over here, which is going to have three properties. First, we are going to consider the chemical potential of this liquid. Then we are going to consider the temperature of the liquid and the pressure. Okay, and then, well, this whole system is made of this liquid and vapor. Okay, so we can think of this as just water, maybe. But the thing here is that we have the same substance, but in liquid and in vapor. So we will have a chemical potential associated to this vapor, the temperature of the vapor, and the pressure of the vapor, where in this case we are going to consider that this system is in equilibrium. So that means that thermodynamic equilibrium conditions say that, well, the temperature of the liquid is going to be equal to the temperature of the vapor. The chemical potential of the liquid is going to be equal to the chemical potential of the vapor. And again, with the pressure, we have a mechanical equilibrium. So that says that the pressure of the liquid is going to be equal to the pressure of the vapor. Okay, so with this, we can recall the Gibbs-Duhem relation. Again, well, this is very well known in thermodynamics. The Gibbs-Duhem relation tells us that the entropy times a differential of temperature minus the volume times a differential of the pressure plus the number of molecules times a differential of the chemical potential is equal to 0. So this relation is telling us that these three quantities are not independent from each other. Okay, so that means that we can establish a function, for example, for the liquid chemical potential as a function of the variable temperature and the pressure, right? So looking at, well, we are in equilibrium conditions, we can set this equal to the chemical potential of the vapor that is also a function of the same two variables, the temperature and the pressure. Of course, in general, we could consider that this chemical potential of the vapor will be a function of the temperature of the vapor and the pressure of the vapor. But, well, looking at in this case, that temperature is just the temperature of the system, we are just going to erase those indices. Okay, perfect. So we are going to establish the two Gibbs-Duhem equations for both systems, right? So that will be the entropy of the liquid times dt minus the volume of the liquid times dp plus the number of molecules of the liquid times d mu equals to 0. And let me just write the index for the liquid here. Okay, so we can establish the second Gibbs-Duhem relation for the vapor as SV dt minus BV dP plus N B d mu B equals to 0. Okay, so just if we solve these equations for the mu, we are going to get for the first one that d mu sub L is equal to minus SL dt plus BL dP all divided by N, L, right? And then for this equation, we are going to get that d mu B is equal to minus SB over N dt plus BB dP over N. And again, these are the ends for the number of molecules of the vapor. So again, just by the equilibrium conditions, we can set these two to be equal, and then we can establish that minus S sub L dt divided by N sub L plus B sub L dP divided by N sub L is equal to minus SB dt divided by NV plus BV dP divided by MB. Okay, so you should know that in thermodynamics it's very useful to define that the entropy can be transformed just by dividing by the number of molecules to get a little s entropy, right? To say that, well, this is just the entropy per molecule or per particle, right? But it's just another way to see things to make it easier. So if we switch these quantities to little variables, we can say that minus S dt plus little b dp, because we do the same thing with the volume, right? We know that the volume can be seen as a v divided by n, just as a little b, which is the volume per molecule. Okay, so this can be equal to minus little s b dt plus little b b dp. And let me just write the indices here, that this is the entropy for the liquid and the volume per molecule for the liquid. Okay, so we are going to circle this result because, well, we can consider that this is already the Clausius-Capeyron equation, but we can establish this as a differential form equation. So we can say that minus SL dt plus SB dt is equal to BB dP minus BL dP. And just by taking a common factor dP over here, we can say that dP BV minus BL is equal to dt that multiplies SB minus SL. Okay, so from here we can see easily that the derivative of the pressure with respect to time of our system is going to depend on the difference of entropies per molecule. So that will be SB minus SL and BB minus BL. And well, we can say that this is already the Clausius-Capeyron equation again, but in general you will find this equation in this form. The derivative of pressure with respect to time is equal to S sub L minus S sub B divided by V sub L minus B sub B, just by multiplying by minus 1 the denominator and the numerator. Okay, so what we can say from this differential equation is that it's going to allow us to find a function of the pressure in terms of the temperature. Okay, so now if we remember from thermodynamics, we know that there is a relation between the heat and the entropy of a system that tells us that, well, in this case, for our system, it tells us that, well, the entropy of the vapor minus the entropy of the liquid is going to be the exchange of heat that goes from the liquid to the vapor divided by the temperature of the system. Recall that again, the temperature of both liquid and vapor is the same. So this is telling us that the change on entropy on the system has to do something with the exchange of heat that goes from the liquid to the vapor. For example, this relation is telling us that if we use the evaporation temperature of the system T, then the difference of the entropies of the corresponding system is going to be equal to the amount of heat that is necessary to evaporate the liquid into the vapor. Okay? Of course, in an experimental way, it is important to mention that the amount of liquid that we have is going to be important to determine the quantity of heat that we need. But you should recall that this, which is the Clausius relation for the entropy, it is considering the upper S, the capital S, right? So we can set the difference of the little s b minus the little s l to be equal to s b divided by n b minus s l divided by n l, like this. And we are going to set this to be equal to an amount of heat that goes from the liquid to the vapor prime divided by the temperature. Okay, so in this case, we are considering that these are entropies per molecule. Okay, so that is an important fact. That means that this quantity little s b minus little s l equals to this thing over here is telling us what is the amount of heat necessary to transform a mole or a particle of the liquid into the vapor phase. Okay, but just per unit of molecule. So that is different because while this expression is telling us the amount of heat necessary to transform the whole system of the liquid into vapor, this is telling us the amount of heat necessary per unit of particle. Okay, and just to finish, we can define this quantity as, well, the heat of the vapor phase divided by Nb minus the heat of the liquid phase divided by N sub L. Again, this is the quantity of heat required to evaporate one particle. Okay? Perfect. So just to resume, the Clausius-Capeyron equation is telling us, well, how to understand the transformation of a liquid into a vapor in terms of equilibrium conditions that the temperature, the pressure, and the chemical potential are the same. Okay, so if those conditions are guaranteed, well, we can use the Clausius-Capeyron equation to see what happens with the transformation from liquid to vapor as the difference of entropies of both systems. Okay, perfect. So I think that with that, I'm going to finish the lesson right now. And I would like to thank you so much for watching the lesson.